Hello, Math 1224. This is Dr. P with Lesson Launch 11.2. So I thought it'd be fun to make a problem about zombies. So I want you to imagine the following scenario. There's a town separated by a river from another town, and there's some kind of nuclear incident that happens down here. So just going to put nuclear something. I don't know what most zombie stories actually begin with, but let's suppose there's some kind of nuclear accident. And it turns everybody on the south side of the river into zombies. And the zombies, because they are hungry for fresh human whatever brains, I suppose, they start spilling across this bridge and into the town north of the river. And as they come across the bridge, they fan out in a triangle that has a 60-degree angle here. Okay? And as they come across the bridge, they start to fan out in such a way that the zombies are very dense near the river, but become less dense away from the river, in such a way that the zombie density is inversely proportional to the distance from the river. So in other words, if the distance from the river is very small, if we were very close to the river, then the zombie density is going to be quite high. As the distance from the river increases and becomes large, the zombie density is going to become rather low. So what we're going to do here is we're going to study the number of zombies within 1 mile of the river. So in other words, we're going to study the number of zombies inside this triangle where the distance of this edge from the river is 1 mile. Now in the last video, you'll recall we looked at mass densities, but densities can be of any kind of thing. It can be a density of mass, it can be a density of a number of zombies, or it can be a density of something else, like people or cows or whatever, in this case, zombies. So, and by the way, I say study the number of zombies rather than compute the number of zombies, because the only information I'm giving about the density in this problem is this, is that the density varies inverse proportionally with the distance from the river. If I don't have any more information than that, then I'm not going to be able to find the actual number of zombies, but I could probably still say something sensible about it. Now, one reason I wanted to put this information here, rather than giving a formula for the zombie density, is I wanted to say a little bit about how we unpack a statement like that. So if we say that something is inversely proportional to something else, then what we're saying is that that thing, so I'm going to call this density at y, and I'll say a bit about why I'm using the letter y in just a minute, but that's going to be some constant over y, and we're going to use y to represent the distance from the river. All right, so when we say rho of y is equal to k over y, that means that if I were to take some particular distance from the river, let's say y miles, then the density of zombies at any point around there is going to be k over y zombies. Let me move over here a little bit. Zombies per square mile. Okay, so this is an area density this time. So the zombie density y miles from the river is going to be k over y zombies per square mile. And we're going to try and set up an integral that'll give us the total number of zombies. All right, so how do we do that? Well, in this case, we're looking at a scenario where the density of zombies is very non-uniform. It is greater down here than it is up here, which means that the idea of just taking a total area and multiplying by one zombie density just not going to work in this case. We don't have a uniform zombie density. But what we can do is we can divide this area up into little strips, and I'm going to create a new color to highlight one of the strips here. Let's see, there we go. Let's use orange for this. Wait, that didn't work. Creating new colors on this sometimes is a bit of a pain. There we go. I'm going to create a strip. Now, why would I choose a strip in that direction, a horizontal strip? Well, the reason I'm doing that is because that is all at one particular value of y. It's all at the same distance from the river. So that means that on this region here, zombie density is uniform. Which means that if I can get a zombie density there, I can just multiply that zombie density by the area of that strip. So that'll give me number of zombies on that strip will equal zombie density. Actually, let me use the symbol for that, rho. That's going to be rho of y times the area of the strip. There we go. And what is the area of the strip in this case? It's going to be, so rho of y is just going to be rho of y for now. The area of the strip is going to be the width times a very small height, or a very small north-south distance, which we're calling dy. And now we just need to do a little bit of geometry to figure out what the width of that's going to be. If this is y units away from the river, so I'm putting a little line segment there and calling that distance y, then what does that make this width here? Well, now we need to use a little bit of what we know about trigonometry. We know that if the angle here is 60 degrees, and that makes half of that angle 30 degrees. And I know for a 30, 60, 90 right triangle, the ratio of the side lengths of this side length to this side length is going to be square root of 3 to 1. So that's going to make this y over root 3. And so the width of that strip is going to be twice that. It's going to be, so I'm going to have rho of y times the width, which is 2y over root 3 times dy. And then if I want the total number of zombies, I'm just going to take that. That's the total number of zombies in one strip there. Oh, by the way, how can I verify that that actually makes sense? Let's do that real quick. So why does this make sense? If I look at the units of everything here, then, well, this is, what does that represent? That represents some number of zombies per square mile. And that represents, remember, that was the width of that strip, so that's the number of miles there. And then dy also represents a number of miles. It's a very small number of miles. So the units are going to come out to zombies per mile squared times miles times miles. That's a number of zombies. So units-wise, this makes perfect sense. I don't know if the problem makes sense anymore. This is becoming kind of silly. If we had a zombie apocalypse in real life, I probably wouldn't be studying the number of zombies. I'd just be getting the hell away from them. But this is a story, so let's see if we can finish the mathematics in the story. Anyway, this is going to represent the number of zombies in that orange strip I drew up there. And then I have orange strips running all the way from y equals 0, which is right where the bridge is, to y equals 1 mile. So I'm going to set up an integral from 0 to 1 of rho of y times 2y over root 3 times dy. And that's going to be the integral from 0 to 1. Now remember, I don't have anything specific for rho of y. I just know that it's inversely proportional to y. So I'm going to put k over y there times 2y over root 3 times dy. And then that's actually going to come out kind of nice. That's going to be, the y's cancel out, so I get 2k over root 3 dy. And then when I integrate that, I'm going to get, let's see, I think the antiderivative is just going to be that k is a constant, so I get 2k over root 3 times y, evaluated at 0 and 1. So I think the number of zombies is going to be 2k over root 3, whatever that is, for whatever value of k we're talking about there. And then, if I knew something about the value of k, I could actually determine the number of zombies. So let's just try an example here. By the way, one funny thing about all of this is that, remember, this represented the number of zombies. Actually, let me do that in a different color. That represented the number of zombies in one strip, right? And then that was equivalent to this. So one thing that tells us is if we chop this area up into equal-sized strips, each equal-sized strip, as long as the strips are uniformly wide, you get the idea, each equal size strip contains a constant number of zombies. It doesn't actually depend upon y. That's kind of interesting. But anyway, let's suppose we do have a limited amount of information about the zombie density. So let's say that we know, for example, maybe some zombieologist comes into the town and determines that, so I'm going to change that to a green color there. That's nice. Okay. Anyway, so a zombieologist tells us, maybe that's a zombologist. That makes a lot more sense. So a zombologist tells us that half a mile away from the river, we have 100 zombies per square mile. So could I then use that to determine the value of k in this formula? And I think that I could do that. So how's that going to work? That means that rho of 1/2 is known to be 100. But according to my model, rho of 1/2 is equal to k, whatever the constant k is, divided by 1/2. So that means that k over 1/2 is equal to 100, and therefore k is equal to 100 times 1/2, which is 50. So then that'll tell me two things. Number one, it'll tell me that the zombie density, y miles away from the river, is now it's not just k over y, it's actually 50 over y zombies per square mile. And the other thing this tells us is I can determine the actual number of zombies within 1 mile of the river. It is now 2k, so that's 2 times 50 over root 3. That's 100 over root 3. And I don't have my calculator next to me right now, but I think that's going to come out to somewhere around 50. I'm going to guess 58 zombies. You can tell me later if I've gotten that calculation badly wrong. I think it's somewhere around 60 anyway. But anyway, not that that seems like a ton of zombies, and actually with 58 zombies, you're getting to the point where I'm not sure a continuous model makes a whole lot of sense, but it can still serve as a decent model for what's going on. And you could do this problem for 1 mile within 1 mile of the river, 2 miles, 10 miles, or whatever, and you'll actually find that because we see this here, because this is our antiderivative, if you want to find the number of zombies within a certain number of miles of the river, that number of zombies is just going to be proportional to whatever the size of the triangle you're looking at. So whatever distance from the river you're willing to consider. Anyway, I'm glad I don't actually live in this town. I don't really fancy the idea of trying to run away from zombies. But anyway, the point of this example, even though it's kind of silly, was to give an idea of how we deal with an area density, because we don't have any techniques yet for integrating over an area, except by cutting the area up into strips. And the way that we did that in this case was we cut this area into strips where each strip had a uniform density. So we might talk about later an example in which the density is uniform, but it's uniform on circles around some center or something like that. Then we would have to slice the area differently. So we might talk about that some in class. But anyway, you've now seen two examples of how we use integrals to work with densities and non-uniform densities, and we'll get more practice in class. See you then.